Let's explore prefix sum and difference arrays, which are efficient techniques for precomputing results. This allows us to handle range queries and updates on arrays with a time complexity of order 1. Here are some common array query problems that we can solve using prefix sum and difference arrays. The first problem is range sum queries. Given an array of integers, we need to compute the sum of elements from index L to R. For example, we might have a function called sum, which takes an array left index L and right index R as inputs. The challenge here is to handle multiple queries with different left and right values efficiently. The second problem is range update operations. Here we want to update all elements in a range from L to R by adding a certain value to them. For example, we might have a function called add which takes an array left index L, right index R, and a value as inputs. The challenge here is to handle multiple updates followed by queries efficiently. Let us discuss the naive approach for solving these problems. For a range sum query, we can iterate through the array from index L to R and sum up the elements. The time complexity for this approach is order n per query, where n is the number of elements in the array. Similarly, for a range update, we can iterate through the array from index L to R and add the given value to each element. The time complexity for this approach is also order n per update. Now let's delve into prefix sums. A prefix sum array P contains the sum of all elements up to the current index in the original array A. The formula to calculate the prefix sum is as follows: P of I equals A of 0 plus A of 1 plus till A of I. The prefix sum technique transforms range sum queries from order n to order 1 time complexity after an initial order n pre-processing step. For example, if we have an array A with elements 3, 1, 7, 4, and 2, the corresponding prefix sum array P would be 3, 4, 11, 15, and 17. Here is how we can compute the prefix sum array. We initialize a prefix array of the same length as the input array. The first element of the prefix array is the same as the first element of the input array. Then, for each subsequent element in the prefix array, we add the corresponding element in the input array to the previous element in the prefix array. This algorithm has a time complexity of order n. Once we have the prefix sum array, we can calculate the sum of any range in order 1 time using the formula sum of L to R equals prefix of R minus prefix of L minus 1. For L equals 0, use sum of 0, R equals prefix of R. This means that after preprocessing, each range sum query becomes order 1. Let's consider an example to understand range sum queries better. Suppose we have an array with the elements 3, 1, 7, 4, and 2. We want to find the sum of elements from index 1 to 3. First, we compute the prefix sum array, which is 3, 4, 11, 15, and 17. Then we can use the formula sum of 1, 3 equals prefix of 3 minus prefix of 0 equals 15 minus 3 equals 12. Therefore, the sum of elements from index 1 to 3 is 12. The concept of prefix sums can be extended to two-dimensional arrays as well. Given a matrix, the two-dimensional prefix sum matrix stores the sum of all elements up to a given row and column. So, for example, if we have a matrix with elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16, the corresponding two-dimensional prefix sum matrix would have elements 1, 3, 6, 10, 6, 14, 24, 36, 15, 33, 54, 78, 28, 60, 96, and 136. The formula to calculate the sum of a submatrix defined by the top left corner are 1, C1 and the bottom right corner are 2, C2 is as follows. Sum of R1, C1, R2, C2 equals prefix of R2, C2 minus prefix of R1 minus 1, C2 minus prefix of R2, C1 minus 1 plus prefix of R1 minus 1, C1 minus 1. Let's understand the difference array. A difference array D contains the differences between adjacent elements in the original array A. The formula to calculate the difference array is as follows. D of 0 equals A of 0 and D of I equals A of I minus 1 for I greater than 0. The difference array transforms range update operations from order n to order 1 time complexity. For example, if we have an array A with elements 3, 1, 7, 4, and 2, the corresponding difference array D would be 3 minus 2, 6 minus 3, and minus 2. The range update operation using difference arrays is very efficient. To add a value to all elements from index L to R, we only need to modify 2 positions in the difference array. We increment diff of L by the value, which increases all elements starting at L. Then we decrement diff of R plus 1 by the value, which cancels the effect for elements after R. These operations are order 1. If we have multiple updates to perform, we can perform all updates on the difference array, and then reconstruct the original array just once. This can be achieved by finding prefix sum of difference array. Let's walk through a range update example. Suppose we have an original array with elements 3, 1, 7, 4, and 2, and we want to add 5 to elements at indices 1 through 3. First, we compute the difference array, which is 3 minus 2, 6 minus 3, and minus 2. Then we update the difference array by adding 5 to diff of 1 and subtracting 5 from diff of 4. This gives us an updated difference array of 3, 3, 6, minus 3, and minus 7. Finally, we reconstruct the array from the updated difference array, resulting in the updated array 3, 6, 12, 9, and 2. This range update is completed in order 1 time. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.